We're continuing with Chapter 3, Differentiation Rules. In this video, we're going to go through Section 3.4, the chain rule. So up to this point in Chapter 3, we've learned some rules for taking derivatives related to specific types of functions, like the power rule and the derivative rules for trigonometric functions. But we've also learned a few tricks that allow us to determine derivatives of functions that occur in different forms, like the sum and difference rule, the constant multiple rule, the product rule, the quotient rule. The chain rule is another one of those tricks that allows us to find a derivative of a function that's in a certain type of form. And it's a very powerful tool. So if we look here, suppose you're asked to differentiate the function, this f of x is equal to square root of x squared plus 1. Well, at this point, we can't differentiate this function. We can't use the sum or difference rule here because we've got this square root. Constant multiple rule doesn't do anything here. The product or quotient rule, well, we can't separate this into a function of x times another function of x or a function of x divided by a function of x. So what do? Well, to calculate this derivative, what we need is, we can write this as we've got a function of x. We'll say u of x is equal to x squared plus 1. All right? So we can write this as f of u of x, right? Like a composite function. So what we need is a method for finding the derivative of a composite function like this. If you have f of u of x, how do you find the derivative of f of x? Or even if we have f of u of g of h of x, right? However many layers of the composite function there are, how do you find the net derivative of that? That's what the chain rule allows us to do. So if you come here, now I'm not going to get into the specifics of how the chain rule is derived or proved. You can look that up on your own. But the chain rule says, so if we've got f of x is equal to f of g of x, right? A composite function like that. Then f prime of x is equal to f prime of g of x times g prime of x. All right. Now, I think trying to explain this to you here doesn't really help. The chain rule is one of those things that if you just work enough practice problems, eventually you'll start to get the hang of it, and then it'll become clear exactly what this means once you've got some experience working problems. Now, we can also look at the chain rule from the perspective of Leibniz notation. So dy dx is equal to dy du times du dx, right? So you have dy du, that intermediate composite function, and then du dx. And you might notice that this is interesting because it's almost like you can cross out this du and you're left with dy dx, right? Okay, but if you come here, so it says comments on proof of the chain rule. We're not going to get into the proof. So here's that Leibniz form again. It says, this is equation 3. It says equation 3 is easy to remember because if dy du and du dx were quotients, then we could cancel du, right? But it says, remember, however, that du has not been defined and du dx should not be thought of as an actual quotient. And so I'm in this video series, in this playlist, I'm really trying to help you as much as I can to understand looking at dy du as a quotient, looking at du as a number, because it does get really confusing when you get to like differential equations and if you're doing research and you read research papers or just when you get to higher level classes, it's almost like it's being treated like du is being treated like it's a number. And this is really convenient to help remember the chain rule, because like if you have, we talk about this in the chain rule, in one of the chain rule videos, but if you have like f of g of h of x, right? So you can do as many layers as you want. If you want to find f prime of x, which we'll say is df dx, Well, what do? You say df dg times dg dh times dh dx, right? That's the chain rule. And so it's like all these cancel and you're left with df dx. That's really convenient. It's interesting. And so you can look at it to help you with the chain rule. You can go ahead and look at it this way. That's fine. And if you go look at the videos on the precise definition of the derivative, you get a very good intuition of what du is, what dx is, and what du dx is. So they tell us what they've told us so far. This is the second time they've mentioned this Leibniz notation and thinking of this as a ratio. This is the second time the textbook has mentioned this. The first time was when we talked about the definition of the derivative function. I think it was the last section of chapter 2. And they mentioned there that we shouldn't think of this as a quotient. It should just be thought of as an operator in the same way like this dx of f of x is the derivative of f of x, or df of x, or d dx f of x, how it's just like an operator. The book told us there that you should strictly think about like dy dx, df dx, just like an operator. And then this is the second time they've mentioned it, and they're kind of telling us the same thing. But again, in the video where we talk about the precise definition of the derivative, you get a really good sense of what dy is, what du is, what this ratio is. And, you know, they say don't think of it as an actual quotient, but I mean, to me, what they should be saying is don't think of it as a specific quotient. In the same way, like if you have infinity, that's not a specific number, but that certainly is a number. And so if dy dx isn't a quotient, then how come we can calculate, like for a certain problem, we could find the derivative and we get like this is equal to 2. That's definitely a quotient, right? It's equal to 2. It's just not a specific quotient. It's not a specific quotient. And again, go check out the video on the precise definition of the derivative. You see what dy is and what dx is. It's like infinity. It's just like infinity, except for something infinitesimally small. Okay, so back to the chain rule. The chain rule can be really tough to understand. That's why we're going to work a lot of example problems. There's 2 like hour-long videos, one with easier level problems, one with harder level chain rule problems. But I'll also go through some of these examples here in this video to help you out. So, all right, we want to find that this is what we started with at the beginning of the section, the square root of x squared plus 1. What is f prime of x? Remember, we can write this as f of u of x. And so if this is written as f of u of x, then what is df du? Because we want to calculate df du dx times du dx. We know how to calculate du dx, right? The derivative with respect to x of x squared plus 1 is just 2x. But what is df du? All that's saying is that you're treating this x squared plus 1 like it's just a variable. So what is the derivative with respect to just this variable? We'll call this u. X squared plus 1 is equal to u of the square root of u. It's this, 1 over 2 squared of u, right? So, but we know what u is. It's x squared plus 1. So just put that here. 1 over 2 squared of u times du dx times 2x. And that's the derivative. Okay, now let's come to this problem here. I'm gonna show you the way that I talk through the chain rule. I don't consider these separate variables like u. I look at it this way. So if we want to calculate the derivative of y is equal to sine of x squared, we say that the function is the sine of something. What is the derivative of the sine of something? It's cosine of that something, right? So just put that, cosine of that something, times the derivative of that something. We've got the derivative of, this is x squared, but let's just keep going with the chain rule. Let's say we've got the derivative of something squared, okay? Because the chain rule can have multiple layers. We can do the chain rule in one problem multiple times. So, okay, we calculated the derivative of sine of something and got cosine of that something. Now we have to do times the derivative of that something. What is the derivative of something squared? It's 2 times that something. Okay? Now, times the derivative of that something. Okay? The derivative of x is just 1, so we don't need to put anything. Right? You see how you kind of use we've kind of always been using the chain rule without stating it. And we don't put anything because, like, the derivative of x squared, something squared, 2 times that something, but we don't continue with the chain rule because there's no more composite function. Because the derivative with respect to x of just x is 1. Okay? So what about the derivative of sine squared of x? What you do is you start at the outermost function type, okay? Like you work from the outside in. What is the most general type of function here? It's not sine, it's something squared. You've got something squared. I know it's hard to see because this is like, remember, sine squared of x is like sine of x squared, right? We've got something squared. What is the derivative of something squared? It's 2 times that something. 2 times that something. Just put that something times the derivative of that something. What is the derivative of sine of x? It's cosine of x. Well, okay, no. What is the derivative of sine of something? It's cosine of that something. Okay? Times, what is the derivative of that something? It's just x. What is the derivative of x with respect to x? It's 1, so we don't need that. So it talks about the power rule combined with the chain rule. To me, this just makes things more confusing. Just learn, if you know the power rule, if you know the quotient rule, if you know the sum and difference rule, then you can put them all together on your own. To me, this just makes things more confusing. Okay, let's do this one here. Y is equal to what? What's the most, the outermost function type here? It's something to the 100th power. Something, when I say something, that's going to be either just x or a function of x. With the chain rule, it's going to be some function of x, right? Most of the time. With the chain rule, it's going to be some function of x, right? Until we get to the end. We have something, right, to the 100th power. Like, this is kind of, you could think of this like x to the 100th power, right? Well, what's that derivative? What's the derivative of something to the 100th power? 100 times that something to the 99th power times the derivative of that something. What is the derivative of x cubed minus 1? 3x squared. There you go. 100 times x cubed minus 1 to the 99th power times 3x squared. That's the derivative. Okay? All right? Here, what they do is you can rewrite this as x squared plus x plus 1 to the minus 1/3, right? Or you can use the quotient rule, but let's use the power rule. All right, so they rewrite the function this way. What do we have here? What's the outermost function? We've got something to the minus 1/3 power, right? We've got like an x to the minus 1/3. This like this something. We could just think about when I'm saying something. Imagine this is u to the minus 1/3, right? U is a function of x. What is the derivative of something to the minus 1/3? Just bring down the minus 1/3, put that something, and subtract 1 from minus 1/3. That's what they do here. Times the derivative of that something. The derivative of, what is the derivative of x squared plus x plus 1? Okay, well, okay, how about, no, here we go. What is the derivative of something squared plus that something plus 1? It's 2 times that something plus 1 times the derivative of that something. But there's no more composite function here. So the derivative of x with respect to x is just 1. You see? Okay, let's come here. What is the, okay, so we're starting here. What is the outermost function? What is the most general outermost function here? Something, some function of t, something to the 9th power. How do you take the derivative of just something to the 9th power? 9 times that something to the 8th power. Put that. And just write that something in there. Just put that something. You don't do anything with it. 9 times that something to the 8th power. Okay. Times the derivative of that something. Okay. What is the derivative of t minus 2 over 2t plus 1? Well, there's no composite function here. So imagine you're saying you've got something what is the derivative of something minus 2 over 2 times that something plus 1? Well, we just use the quotient rule there, right? So this could be drawn out. They're trying to confuse you. They're making this more long and drawn out, but you just have to follow the steps that you know. They use the quotient rule. Okay, done. Times the derivative of that something. Derivative of t with respect to t is just 1. There's no composite function here, you see? Okay. What about this? Y is equal to 2x plus 1 to the 5th times x cubed minus x plus 1 to the 4th. Well, we can use the product rule here. You got one function of x times another function of x, okay? Now you just have to use, the key to this is using brackets, big brackets to really box everything off and separate everything. What is the derivative of this? We have to use the chain rule here. We have something to the 5th power. So 5 times that something to the 4th power times the derivative of that something. The derivative of 2x, there's no more composite anymore. 2x plus 1 with respect to x is just 2. So that's the derivative of the first. Multiply that times the second. Plus the derivative of the second. Chain rule again, something to the 4th power. Do that. Times the first. And then you have to just simplify everything. Okay? Now here, this is where we're going to actually, we talked about in section 3.1 that I wasn't sure why they didn't give us the official definition for derivatives of exponentials like 2 to the x, 3 to the x. They just gave us the derivative of e to the x. And this is where they give us that official definition. What they do is they say, okay, differentiate y is equal to e to the sine of x. Well, okay, they don't give us that definition here. They show us this method first. So what is the derivative of y is equal to e to the sine of x? What is the outermost function here? We've got a composite function here. We've got e to the something power, some function of x, right? What is the derivative of e to the something? It's e to the something. Just put e to the something, e to the sine of x, times the derivative of that something. What is the derivative of sine of something? It's cosine of something, times the derivative of that something. What is the derivative of x with respect to x? Just 1, so we're done. E to the sine of x times cosine of x. That's the derivative. Okay? So now it says with that in mind, with that technique in mind, it says we can use the chain rule to differentiate an exponential function with any base, not just e. All right, so in pre-calculus, it told us that we can represent b, so a base b. We can represent this number b as e to the natural log of b, right? E to the natural log of b is just b, right? Okay, so let's write this as b to the x. So b to the x power is e to the natural log of b to the x power, which is e to the natural log of b times x, right? So let's differentiate that, because that's where we're looking for a general derivative of this, of b to the x. So the derivative of b to the x power is what? So how do we calculate this derivative with respect to x? We've got e to the something, right? E to the natural log of b times x times the derivative of that something times natural log of b. But what is e to the natural log of b times x? That's just b to the x. So that's where we get. Here's another, we can add this to our toolbox now. The derivative with respect to x of just any base to the x power is just rewrite the b to the x times natural log of b. And if b is equal to e, natural log of e is equal to 1, right? So you get what you expect. Natural log of e to the x is just e to the x. Okay? And then here so we haven't worked an example problem with multiple layers yet, but I wrote out that formula how if you have like dy dt and you've got multiple layers, you just use those multiple layers. You just go one layer after the other, right? Remember how we wrote this out? So if you have, what is the derivative of sine of cosine of tangent of x? You start with the outermost function. The outermost function here is sine of something. What is the derivative of sine of something? Cosine of that something. Just write that something. Cosine of that something times the derivative of that something. What is the derivative with respect to x of cosine of something? It's minus sine of that something, right? Minus sine of that something times the derivative of that something. What is the derivative with respect to x of tangent of something? It's secant squared of that something, okay? Secant squared of that something times the derivative of that something. What is the derivative with respect to x of just 1? What is the derivative with respect to x of just x? It's 1, right? Once you get to the point where there's no more composite function, you can stop. But if it's hard for you to notice when to stop, then just keep using that something, that something talk. Just never stop saying the derivative with respect to this of something, of something, of something. And then you'll get to the end and you'll say, well, I'm just taking the derivative with respect to t or x of x or t. So it's just 1, so I'm done. Okay? So you can use the chain rule twice, 3 times, 4 times, it doesn't matter. All right, let's do this last example. So y is equal to e to the secant 3 theta. What is the outermost function here? E to the something. E to the something. What is the derivative with respect to theta? This is y of theta, right? This is y of theta. What is the derivative with respect to theta of e to the something power? When we're saying something, we're suggesting that that something is some function of theta. It's e to that something times the derivative of that something. What is the derivative of secant of something? It's secant of that something times tangent of that something times the derivative of that something. What is the derivative with respect to theta of 3 times something? It's just 3 times the derivative of that something. What is the derivative with respect to theta of just theta? It's 1, right? That's the end's kind of confusing there. If we had 3 times x squared plus 2x minus 4, and let's say we didn't want to differentiate this 3, or distribute this 3. We wanted to practice the chain rule. Well, we've got 3 times something. What is the derivative of 3 times something? It's just 3 times that something times the derivative of that something. 2x plus 2. Okay, and here they talk about proving the chain rule. We're not going to get into that. You're welcome to look into that on your own. And so, yeah, so you might be a little confused. What you need to do is there's 2 example problem videos, one with easier level problems, one with hard level problems. Each video is like an hour long each. Try each problem slowly on your own before you look at the solution. Try it as hard as you can. Pause before the first problem. Try it as hard as you can. Watch the solution. You're going to get frustrated because you didn't do it right. Try and learn about what you missed. Then try the next problem on your own. Keep doing that. Eventually you'll get it. It'll become clear what's going on.